Welcome to Homework Lib.
Hi, so in this case we're going to have an unknown weak acid, HA, which has a Ka equal to 5.61 times 10 to the minus 6. That means that the pKa of this acid it is going to be 5.25. And we know that we're going to have a total amount of 9 millimole, which is 9 times 10 to the minus 3 mole, of this substance of HA that is going to react with a strong base. So essentially our reaction is going to look like this, producing water plus A minus. So at the very beginning, we're going to have this table in millimole, just for sake of simplicity. We're going to add 9 of my unknown acid and 1 millimole of the other one. We start with 0 and 0. So the amount of change it is given by the OH minus, so plus 1, plus 1. And at equilibrium, we're going to get 8 millimole, 0, 0, and 1. This means that we have a acid with its conjugate base present in the solution with the following amounts. In this first case, we're told that we're not told any volume, but that doesn't matter. Actually, that is something that a lot of time confuses students, but you can see that in this case, the amount of mole of A minus divided by the amount of the total volume divided by this, you can see that the volumes are going to cancel out whenever we are below the equivalence point, and the only thing that matters is the amount of mole that we have. In this case, we could leave it at millimole, as they are, because the units are going to cancel out when we plug this into the Henderson-Hasselbalch equation. So remember, Henderson-Hasselbalch equation is pH is equal to pKa plus the logarithm of the concentration of A minus divided by concentration of HA. The pKa that we found was 5.25 plus logarithm of A minus is 1, HA is 8. Logarithm of 1/8, which is equal to minus logarithm of 8 if you want. So the pH for this result is going to be 4.30 347. So this is the pH when we have added only 1 millimole of the strong base. Now, for the part B, the next question. More strong base is added until the equivalence point is reached. What is the pH of the solutions at the equivalence point if the total volume is 70 milliliters? So in this case, we now need the total volume because all of the compound is going to react. So again, we can go ahead and write down our ice table, producing water plus A minus. And what we are going to do is I'm going to do this ice table first in mole, and then we're going to convert the results into concentrations. So of HA, we started with 9 millimole. At the equivalence point, that means that we have added 9. We have 0 and 0. The change is going to be minus 9, minus 9. This is something close to 0, something close to 0. Water, it doesn't matter because it's a pure substance, plus 9 millimole. So that is the amount of A minus that is going to be generated at the equivalence point. Next up, we need to look for the reaction that involves the A minus that we have present. First of all, let's calculate the concentration of A minus, which is going to be 9 times 10 to the minus 3 mole. divided by the 70 milliliters, which is 70 times 10 to the minus 3 liters. This gives us a concentration of 0.128 molar. Let's call this C0 for sake of simplicity when we draw the new ice table. So now A minus is going to react with water to generate OH minus and HA. With this, in our ice table, we have C0. The amount of change is going to be minus X, C0 minus X. Initially, we have 0 of both of these guys. Here, the change is going to be plus X, and X, and X. Cool. So, with this result, what we can get is that, first of all, the value of X is going to be very small. Next thing is that if we write down the equilibrium constant for this reaction is concentration of OH minus times concentration of HA divided by concentration of A minus. But what happens here? This is not the reaction for Ka. This is the reaction for Kb. Okay? So replacing the values at equilibrium, we get X divided by C0 minus X, which is X squared divided by C0 minus X. Now, the other thing that we need to do is to find the value for Kb. We know that Ka times Kb needs to be equal to 10 to the minus 14. Recall that that is Kw. So Kb is 10 to the minus 14 divided by the Ka. That in our case is 5.61 times 10 to the minus 6, giving us a value of 1.786 times 10 to the minus 9. Okay, so we know that the value for Kb is going to be quite small, right? Since Kb is going to be that small, that means that X is going to be very small. So we can make the approximation that X is going to be much smaller than C0, which means that C0 minus X is approximately C0. So our equation now becomes Kb is equal X squared divided by C0, thus giving us the value for X equal to a square root of Kb times C0. If we replace the values, remembering that C0 is this number, C0 is 0.1286 molar, and we plug both of these guys into this equation, we get the value for X as 1.51 times 10 to the minus 5. Actually, 155, just to 552, just to be super thorough about it. Times 10 to the minus 5. And what is X? Well, if we go back to our ice table, this X is the concentration of OH minus at equilibrium. So this is equal to concentration of OH minus. Finally, with this result, we can calculate the POH. Recall that this is minus logarithm of concentration of OH minus. This gives us a value of 4.82. And we get the pH as 14 minus POH, which is going to be 9.2. And that is going to be our final answer. Thanks. Wait, sorry, 9.12, 9.18. Yeah, sorry, forgot that I didn't round it up the last one. So 9.18. And that is going to be our final result. Now for it. Thanks.